All right, take two. Hi guys, this is Objective 3.1. We're starting Unit 3 today. More on functions and way more on functions. So today's topic is increasing, decreasing, and piecewise functions. These things are tricky, but they don't have to be. So pay attention and think about it. And if you have questions, you should ask them. All right, so the essential questions are here. How do you determine on the intervals on which a function is increasing, decreasing, and constant? And then number two, how do you graph piecewise functions? Those are the main ideas here. So let's first talk about, remember what a function is. A function passes the vertical line test for every input. For every x, there's exactly one output. Okay, so don't forget that. That's what a function is. All right, so we're definitely talking about functions. And let's do some defining of an increasing function. So if I were to take an x and y axis here, here's x-axis, here's y-axis. So I'm going to zoom in a little bit so we can look. All right, and I put on here point A and point B. You would consider A to be less than B as we read that graph left to right, correct? Now, if a graph is increasing, we would say that it would be increasing if it was doing something like that, correct? It's increasing. And how do we know it's increasing? Because our function value for A is lower than our function value for B. When I plug in a B, I get out a higher value, right? So if A is less than B and the value of the function at A is less than the value of the function at B, then the graph is said to be increasing over the interval between A and B. Okay? It's said to be increasing over the interval A and B. Now that's the tricky part. People always think, but it's increasing, that means it's going up, so why aren't we talking about the y's? Well, the function is going up, right? The function is increasing as we read the graph from left to right. If we were reading the graph from right to left, then the function would be decreasing. What we want to know is over what intervals, that's domain, is the graph increasing. All right, so there's the definition of increasing. Let's do decreasing. So we'll do another picture here, and hopefully this will be a little bit intuitive here. All right, so if I put A here and B is here, all right, we can then say again, A is less than B. Now, if a graph is decreasing, what's going to happen is the output for the function value, the function's value at A, is going to be greater than the function's value at point B. And the graph might do something like that. So if A is less than B and the f of A is greater, the function's value is greater at A than it is at B, then the function is decreasing over the interval between A and B. See that? All right, so that's decreasing. So again, look at that. I'm talking about an interval from left to right. Increasing, decreasing from left to right. Now let's look at a constant. All right, so let's say here we have an x and a y here. Those are x and our y. Should always remember to do that. All right, and I put A here and B here. So we'll say this. If A is less than B, right, left of B, and the function is constant, here's the point. The function's value at A is right there, and the function's value at B is also right there. So we would say if the f of A is equal to the f of B, which is the only other option we have, it can be less than, greater than, or equal to, then the function is constant over the interval between A and B. Okay, now what we have to remember all the time is that when we're talking about intervals of increasing, decreasing, and constant, that the intervals remain open. Open, open, open. So no brackets, even though those are closed points, no brackets. When we're talking about intervals of increase, decrease, and constant, you always keep your intervals open. And you're going to see here in just a second why. Let's take a look at these examples. So it says determine the intervals on which the function is increasing, decreasing, and constant. And we have these two piecewise functions here, and we know they're piecewise functions because they're graphed in little pieces, and they're different kind of functions at different places on the domain. All right, and so let's take a look at this first piece, and I think I'm going to color code. So when the graph is constant, I'm going to go ahead and graph in orange. So here we have a constant section of the graph. So between -5 and -3, right? This is -5, 2, and this is -3, 2. The function's value at all of the points even in between that are at y equals 2, right? And so we would consider that a constant interval. So between the -5 and a -3, the function is remaining constant. That piece of the function is constant. Okay, now let's look at another piece. I think I'll do this next piece. If it's increasing, I'm going to use green. So if you look at this section here, right, that's definitely increasing between -3 and -1. What's happening? At a -3, we're at -4, and at -1, we're at +4. So as I go from left to right, that graph is increasing over the interval between -3 and -1. It is also increasing over here again between 3 and 5. You can see between 3 and 5. Now, typically you would write a union here because that is an actual union. I will say though, for your Canvas today, if you were typing in answers for a question like this, just go ahead and do this: -3, -1, use a comma, and then 3, 5. Okay, you can't type in the union symbol, so don't type like a capital U or anything. Just use a comma to space them out. All right, and so here's a point where I want to discuss why we don't use a closed bracket on this. So here we are at x equals 3, right? X equals 3. And that's the point 3, 2. Now, does that belong to this blue piece? Or does that belong to this red piece? Because let me tell you, it can't belong to both of them, because then it's not a function. Because this is a different graph, or a type of graph, than that. This has got a negative slope. This has got a positive slope. They're different. And so a single point, or a turning point, or a stopping point isn't considered increasing, decreasing, or constant. It's just a point. So we're always going to leave our intervals of increase, decrease, and constant with open, so parentheses. So here we can see between 1 and 3, you got a jump in your domain here where there's nothing being graphed. We call that a jump discontinuity. Between 1 and 3, our graph is decreasing, right? So we would say that this graph is decreasing over the interval 1 to 3. And that covers all of the pieces. Okay, so let's take a look at this next one. You've got what it looks like here, a parabola, and then a constant, and then a positive slope linear equation, and then another constant. So let's identify. Go ahead and try to do it without me. So press pause and give it a go and see if you can identify all your intervals of increase, decrease, and constant. Then press play and let's see how you did. So I'm going to assume that you gave it a go. All right, so I'm going to start with the constant section. So here's a constant section of the graph where the function's value between -6, -2, and -3, -2. All of these points right here, the function value is remaining constant. So between -6 and -3, we're constant. And then again, up here, there's a big jump up here between -2 and infinity. We're also constant. And so we have two pieces of this piecewise function that are constant. So between -6 and -3, open, and a union. Again, with your homework, just put a comma between them. And between -2 and infinity. And we're just assuming infinity because of that arrows indicating that that function's just going to continue along that path. So there are our constant sections. Now let's do our increasing sections. So here we have this parabola, and it's coming up, up, up as I'm reading it from left to right. It's coming up, 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 up until it hits the vertex, right? So that's increasing. So basically, until it gets to the vertex at -8, it's increasing. So I could say that it's increasing from left to right, negative infinity, all the way to -8. And then the graph decreases, and then it's constant. And then here, right here, there's a really strong increase between -3 and -2. So it's also increasing across -3 to -2 on your domain. The last piece is this piece here where the graph is decreasing, and that's across the intervals between -8 and -6. So -8 to -6, the graph is decreasing. And there you go. All right, hope you did well. Let's move on. Okay, this next section, example 2, says graph the function. Give the intervals on which the function is increasing or decreasing. So I'm just going to graph these by hand really quick because I'm pretty familiar with the parent function of a quadratic. So I'm just going to graph that really quick. And then I'm just going to use the vertical reflection and then the vertical shift to regraph it. So f of x equals x squared looks like this. And now I'm going to flip it upside down with the vertical flip. So those 2 points are going to come down. Those points are going to come down here. And so I'm just doing a little bit of movement here. And then it's going to go up 5. So I'm just going to take all those points up 5. And erase. And graph. All right, so we have a little parabola. And our job is to determine over the intervals which the function is increasing or decreasing. All right, so it's increasing here, right? And you know as this continues, this is going to continue to decrease as I go to the left, right? But we read things from left to right. So as we're coming to the right, that graph is just constantly increasing until we hit the vertex. So it's increasing from negative infinity until we get to 0, which, remember, it's all the way to here at x equals 0. And then it turns, and it goes down forever. So as x gets very large, y gets very small. So from 0 all the way to infinity, that function is decreasing. Notice I didn't include the vertex because the vertex is the maximum point. It's neither increasing nor decreasing. All right, next one. Excuse me. All right, let's look at this next one. So this is an absolute value function. So I'm just going to go ahead and remember how to graph the absolute value of x. So 0, 0, absolute value 1, 1, absolute value 2, 2, absolute value -1 is 1. And so there's the parent function. Now I'm going to go ahead and use my shifts. So this is a horizontal shift. It says to push the graph right to. So all these points are going to go right to, and then push the graph vertically up 3. So I'm going to take this vertex right to and up 3, and then I'm going to go ahead and plot the rest of the points. Also, that's your HK. If we were doing this, this would be your HK. So your vertex would be at 2, 3. And so that it's just, I don't know if you remember how to graph it like that or not, but there it is. So there's our graph, and I think I meant to graph that in black, so I'm going to go ahead and switch it to black. And we are going to identify our intervals of increase and decrease. So first what this graph is doing is it is decreasing. So from negative infinity all the way to the vertex at x equals 2, this graph is decreasing as I move. It's coming from really high and going really low. So it's decreasing over the interval between -1 and 2. And then it turns and it begins increasing on the other side of the vertex all the way to infinity. So that would be from not -2. Guys, that's a positive 2. So 2 to infinity. Sorry about that. Okay. So you're either going to have to remember how to graph things or get out Desmos and just graph it. Use Desmos to graph it. Or use your graphing calculator to graph it. Okay, so now let's go to some piecewise functions. So what are piecewise functions? Piecewise functions, I mean, when you see them written out as an equation, are really funky looking because it has like, it might have two different functions in the function, or two different pieces, and they look totally different. Might have 3 pieces, 4 pieces, 5 pieces, depends. All right, but each piece, or to be, remember, it had to be a function. It has to pass the vertical line test. So the x value can only belong to one piece of the multiple pieces that exist. So let's take a look at this, and I'm just going to color code here. It says for the piecewise function, find the function's values. So we have the h of x is equal to this first piece here. So I'm going to call this piece 1. So the h of x is equal to -3x minus 18, but we have conditions here. X has only for x is less than or equal to -5. So if I were to graph that, that means here, if this was -5, that I would only be able to graph this blue function in that part, and I'd have to keep that open, by the way, because that says less than -5, so I couldn't include x equals -5 in that first piece of the function. Okay, so that's where that function would go. And then let's take a look at this next function here. This looks like a constant function. So if I have h of x is equal to 1, well, it's equal to 1 over this defined section of the domain, and that would be between -5 equals to -5. So notice that the -5 doesn't belong to the top function, it belongs to the second function because of the equal sign less than 1. So that means it would be between here and here. That would be where I would graph that piece of the function. Okay, and then the last one I'll do here in green. All right, so this would be the h of x is equal to x plus 2, but only over the domain where x is greater than or equal to 1, and so that would be a bracket there, and that would be going left to right. Now, before we were talking about open and closed intervals, we're keeping the intervals open. That's when we were talking about the behavior of the graph. Is it increasing, decreasing, or remaining constant? Now what we're actually doing is graphing or finding values. Okay, so now we can open and close circles all we want because we're not describing the behavior of the graph. Okay, so let's take a look at this. We have to find the h of -6. All right, so that's our x value. So which piece of the function does it belong to? Well, it's here. That's where -6 is. So that means we'd have to plug it into this first function here. So we're going to do the h of -6 equals -3 times -6 minus 18. And so that'd be -18 minus 18. So the h of -6 is -36. So that means if I were graphing that, it'd probably be way down here somewhere on the graph. So there's that value. Let's look at this next value. It says find the h of 0. Okay, well 0 is right here, right, for x. So that means we're going to plug it into the second value. So we're going to do, okay, the h of 0 equals 1. Okay, so there we have that. That's already done. Oh, actually, I should have plugged that in here. The h of 0 equals 1. That's the equation. Doesn't matter what x I plug in, the y is always 1. So there's that piece. All right, so let's take a look at the next one. So it says find the h of 1. So that has to belong to the third function, piece of the function because x that's defined on the domain for x is greater than or equal to 1. So I'm going to plug it into my green function here. So we're going to do the h of 1 is equal to 1 plus 2 because I'm plugging it into this function here. All right, so that would be the h of 1 equals 3. All right, I'm going to go back and do some highlighting here. So there's the h of -6. Here's the h of 0. Here's the h of 1. The last one we have to do here is the h of 4, and that would be way over here in this domain. So again, we'd plug it into that third function. So we'll find the h of 4, which is really hard to do. I mean, 4 plus 2, who can do that arithmetic these days? Silly sarcasm. And there we have that. And so that's how you find specified function values. You just really have to look at the conditions that are set here in the piecewise function over the given pieces of the domain. Okay? All right. So there's that. That's not too bad, right? That's pretty good. Let's take a look at this last piece, and then we're going to graph it. We're going to graph it by hand, and then we'll plug it into a graphing calculator. So let's take a look at, we got these 3 pieces here. So I'm just going to lightly on my graph separate my domain. So I'll start with blue here for x is less than or equal to -2. Okay, so that's going to look something like that. I'm going to take this off in a second because that's not actually part of my graph. I'm just separating my domain over my intervals. I'll go to red next. So for my second piece here, I'm looking at x is between -2 and 3, but open because there's no equal sign in either of those inequalities. So that would be the section where I'm going to graph that middle piece, x plus 1. And then this last piece here we'll do in purple for fun. All right, so we're going to do this third piece for x is greater than or equal to 3, and so that would be from here to here. Again, you wouldn't really do this on your graph. It's just a visual to help you think about it. So let's graph. We'll start with the blue. We're going to graph f of x equals 4. But only, that's a constant, right? For x is less than or equal to -2. So maybe I'll just do this. Here's x, and here's my f of x. So I can pick -2, and I'm going to close it at -2 because it does say to include -2 as the value for x. And it doesn't matter if I plug in a 2 here. The f of 2 is 4. -2 is 4. I'm also going to do -3. The f of -3 is also 4. So at 2, -2, 4, closed, and then 3, 4, and it's just a constant. There's y equals 4. So there's our first piece over that domain. So now I'm going to erase this because I don't need that there. It doesn't belong there. Let's go to the second piece here. We're graphing this f of x equals x plus 1. Well, that's so easy to graph, right? Because your y-intercept is 1. And your slope is 1 over 1. So just remember that we have to keep it between the values that we were provided, and also to remember that we have to keep our points open at x equals -2 and x equals 3 because there's no equal sign on those inequalities, and so that would be this piece of the function there. And so let's just make sure that we have a function here and we haven't broken the function rule. All right. So I'm just doing a vertical line test here, and it looks to me like I'm okay here on the left side because the -2, it's defined up here at -2, 4, and down here at -2, -1, it's undefined, and that's why there's an open circle there. So still a function, passes the vertical line test because it's open on the bottom and closed on the top piece. Let's do the last piece. So we have f of x equals -x for x is greater than or equal to 3. So I'll just do a little table of values, although you should probably be able to do this in your head, f of x. But we're going to start at +3, and because it says greater than or equal to, we're going to keep it up closed point there. So 3, so the opposite of 3 would be -3, and we'll plug in a 4, and the opposite of 4 would be -4. So at 3, 3, 3, negative 3, it's closed. And at 4, negative 4. And then it's just got a slope of negative 1. And so your graph is going to go like that all the way to infinity. All right, and so there's that function, and that one wasn't too bad because those were all linear, so pretty easy to graph. Okay, let's check with a graphing calculator. So I'm going to go to Desmos here, and I bet I'm going to have to erase all these functions. Oh no, I erased them. Okay, so how do you type a piecewise function in Desmos? It's really simple. You just type each piece as in a different equation. So I'm going to do the first one here. So y equals 4. You could also type f of x if you want, but that just complicates things. Now, so did you see what happened is it graphed the whole equation, left to right. But we had to keep that confined to the domain x is less than or equal to negative 2. So to do that, what you need is the curly braces. So we're going to go to the curly braces here, and it gives you both of them, and then we'll go back here and we're going to just put in x is less than or equal to negative 2. And you can see there now that it has graphed just that piece, and so that's how you confine the function to just the section of the domain that you want to confine it to. And you can see that when I scrolled all the way across that negative 2, x was actually equal to negative 2. You can see that when it's x is negative 2, y is 4. All right, second piece was y equals x plus 1. So we're going to do y equals x plus 1. And there we have that. And again, you can see the whole section, that whole line. And that's not a function because it fails the vertical line test. So we need to set our limits on this next piece, and remember that x was in between negative 2 and 3 here and not inclusive. So let's go get our curly braces to put our conditions, and then we're going to start with negative 2 less than x less than 3, and there we have that piece of the function. Now I just like to cruise along the function to make sure that you can see here at x equals 3, the graph is undefined because it's not allowed to equal 3, and then if I go down to the bottom at x equals negative 2, it's also undefined. So that's good because we had x equals negative 2 up here at the top, defined on this first piece, not defined in the second piece. Let's put in the third piece. So that one was y equals negative x, and again we have to confine it to that section of the domain where that piece of the graph is defined. So we'll get our curly braces, and this one was at x is greater than or equal to 3, and there you can see that piece of the graph, and that looks a lot like the graph that we just did. And let's just make sure that our graph is defined at x equals 3, and you can see that it is. And so that's how you use Desmos to do it. If you're going to be using your TI-84, which would be really good if you have it, I'm posting a video on Canvas in the resources that shows you how to type the piecewise function in so that it looks exactly like this. And you just go to your y equals and you choose the piecewise function, and you just have to go to math and find piecewise. And then it also shows you how to find these conditional statements, how to find those so you can type them in, and then you can look at the graph on your TI-84, which is a really cool trick, so you should definitely do it. All right, that's all we have for you today. You have 7 or 8 problems to do on Canvas today to show us that you understand this topic. And that's what we have. We'll see you later. Bye.